This is our last lesson in the quadratic algebra unit. This is 3.10, which is on quadratic applications part 2. So exactly the same as the last video, but we're just doing different examples now, where we're going to, number one, decode the word problem so that we can create a quadratic equation. Number two, we're going to expand and simplify that equation so that it's in a form where we can then factor. And then number three, we're going to solve. Okay, so I'm just going to jump right into it because these questions are a little bit complicated. And I have a video limit of 15 minutes. So example number one, a garden is enclosed on 3 sides using 60 meters of fencing. The remaining side is formed by the wall of a garage. What dimensions enclose 450 meters squared of garden? So I have a diagram that I just drew just to visualize. They're basically saying you have a garage wall right here, and against that wall you're going to build a garden, and the garden only has fencing on 3 sides. So that's this side, and this side, because you're not going to put a fence against the wall of a garage because there's already a wall there. That fencing is 60 meters in total. So they kind of gave you the perimeter of this 3-sided rectangle. We know that perimeter would be length and width. So here I have my 2 widths, and then this long side would be my length. But when we write length and width as 2 different letters, it's really hard to solve an equation, only one equation, when you have 2 different letters. So it would be much better if you can somehow change one of the letters to suit the other letter, and that's why they gave you the 60 meters. If I just say that 2 of these W's and the length, so 2 W's and the length is 60 meters, I can then represent the length with W's. By moving the 2W to the other side, it becomes a minus. I now have the length where I don't have to write it as L. I can then write it as 60 minus 2 W's, and look, you have all W's. So having all one variable makes it easier to solve for that variable. Now, I still need an equation that I'll need to factor and solve from, and that's where the 450 comes in. So the 450 meters squared represents the area. You can tell by the meters squared. And since this is a rectangle, you're going to go area is length times width. I know that the area is 450, the width is just width, and now the length I can represent in terms of a W, and now I have an equation with all W's. So this is the initial formula. You then want to manipulate it so that it's in a form that you can easily factor and solve, which means that you need an equals 0, and there shouldn't be any brackets. Everything should be opened up. So let's expand and simplify everything. W times 60, W times negative 2W is 60W minus 2W squared. Make sure that your W squared goes first and is usually a positive. So since it's a negative, I'm thinking I'll probably take this entire term and bring it to the other side, which makes it a positive. I may as well just bring the 60W over to the other side as well. So it becomes negative 60W. That 450 didn't move, so it's still positive. But that equal sign is right here, and there's nothing else on this side anymore, so I get an equals 0, which is what I want. This now looks like a trinomial, and it looks like a complex trinomial, but I can see that I can pull that 2 out from each of the terms. So I'm going to common factor first, and I'm actually left with a simple trinomial that I can then factor further. Okay, so 2 numbers that multiply to 225 and add to negative 30 are negative 15 and negative 15. This step concludes our factoring. Now we're going to solve. So from each of the brackets, I jumped the intermediate step and went right away into W will represent the opposite of whatever is inside the brackets, which is positive 15. We have the same answer either way, and then we can use that answer to then solve for length, because 60 minus 2 15s will give you 30 for the length. That means that our dimensions are going to be 15 meters and 30 meters. Now going into a slightly more complicated question, Example number 2, a photograph is measured by measuring 12 centimeters by 8 centimeters is to be surrounded by a mat of uniform width before framing. What this means is, think of this smaller rectangle as the picture. It is 12 centimeters by 8 centimeters. Before you frame a picture, in order to make it look bigger, they put like a paper white frame around it. So it's just paper. And it's uniform in width, which basically means that it's the same width all the way around. And I just use X. You can use W. It doesn't really matter. But now it's created a larger rectangle. And so I'm just going to show you how I got this 12 plus 2x. Do you see how like the original photo was 12? And then you've extended it this way x and this way x as well. So the entire width of the larger rectangle is going to be 12 plus 2x. And you do the same thing on the side. So 8 was the photo, but then you've extended this way x and down this way x. So the total longer side on, the total width of the larger rectangle is going to be 8 plus 2x. Now, what do I do with all that information? I'm still trying to decode this word problem to create an equation. The area of the mat is to equal the area of the photograph. That right there, that sentence right there is my equation. The area of the mat is to equal the area of the photo. Okay, now we know the area of the photo, which is the yellow, it is 12 by 8. But the area of the mat represents just this, like, I can call it a frame, I guess, portion. Now, how do I find that? That requires a little bit more work. You can take the larger rectangle's area and subtract the smaller rectangle's area, and you'll be left with the kind of paper frame around it, which represents the mat. So that's the area of the larger rectangle, subtract the area of the smaller rectangle. Now the larger rectangle's dimensions are 12 plus 2x for the length, 8 plus 2x for the width, minus the area of the photo, which again was 12 by 8, is equal to, and all of that was just the mat. So all of this is the area of the mat, is equal to the area of the photo. So equal to the area of the photo. That is my initial quadratic equation. I now have to put it in a form where I can factor it, and then I'm going to solve. So open up by expanding, doing distributive property, expanding and simplifying. This right here is the 96, and then we got the 96 over here. Make it equal to 0, bring everything to the other side. So you see I'm going to have a negative 96. I also made sure that the x squared term goes first, and then the one with the x goes second, and all the numbers with no x's go at the end. And after simplifying this, I get what looks like a complex trinomial, but I notice that the 4 can come out of each of the terms. So I factored out a 4, and it makes it a much easier simple trinomial that I can then factor. Two numbers that multiply to negative 24 and add to 10 are 12 and negative 2. And when I solve for those two, x is the opposite of this number, negative 12, and the opposite of this number, which is 2. So I have two different answers, but when we think about what x actually meant, which is the width of this paper mat, this one doesn't make sense. How can you have a negative 12 centimeter width of a mat? So we call it inadmissible and we discount it. We don't look at it anymore. Our answer is 2 centimeters. So the question itself asked, find the width of the mat. And that's what it is, 2 centimeters. All right, now let's go three-dimensional. An open-topped box is made from a rectangular piece of cardboard with dimensions 24 centimeters by 30 centimeters by cutting congruent squares from each corner and folding up the sides. Okay, this is a piece of cardboard. It measures 24 by 30, and what they're going to do is they're going to cut and like basically throw away each of these corners, which are squares, and we don't know what the dimensions of the squares are, but they should be the same because it's a square. And so I just represented it by x. Okay. When we actually cut out each of these, we're left with kind of like this shape right here, like this, kind of like a cross, a really fat cross. These represent, so this side, and this side represent the sides of the box, the four sides. This middle part is basically the bottom of the box. So these dotted lines right here, here, and here are going to be where the folds are, and these flaps fold upwards. And so glue is going to go on these two sides, and they're going to glue together to make the one side of the edge of your box. Now they're telling you that the box has a volume of 1,040 centimeters cubed. So I'm creating a volume formula, which is length times width times height. That's way too many letters. So let's represent them all by one letter. The length was 30, but because you cut off this X piece and this X piece, your new side of your box, the bottom of your box, is 30 minus 2 X's. So right here is your length. We do the same thing with your width, which used to be 24, but you've now chopped off this portion and this portion. And so your new fold right here, which represents the side of your box, is 24 minus 2x, which is right here. And then the height of the box, once you glue these two sides together, is going to be right here, which is just x. So that is your equation. You're going to expand. So I've done the expansion of these two binomials, keeping it in brackets, and then you're going to take the x and expand it into that answer. So you get something like this. Move everything onto one side so that you get a 0, and make sure that the highest degree goes first. And then there we go. That's the x. And then lastly, the negative 1,040. Now here's the thing. This is a cubic equation, and so we don't really know how to factor something like this. It's something that you're going to learn in grade 12. So I figured I'd show you how to use graphing technology in order to figure out the 3 answers. Actually, there's 3 answers this time instead of normally we have 2 because it's a cubic. So how did I get these 3 answers? Well, using graphing technology, I'm just going to show you. This is what a cubic, so a degree 3 would normally look like. If I write it as a factored form like this, you'll then see that -1, so the opposite of this number, is represented right here. Okay, and then we have the +2, opposite of that number right there, and then the 4. So when we solve for each of the things in the bracket, those actually represent graphically the x-intercepts of your diagram. So when I use the same equation that was in the box question, this one right here, this is just an expanded version of this form. They're not the same. This was just an example, but I'm saying this form is called factored form, and this is just an expanded form of factored form. And so if I graph this guy, it's huge. Like, I'm going to have to zoom out just for you to see the shape of the graph. And I don't really care too much about the shape. What I care about are the intercepts. So the x-intercepts are 2, 7.4, and 17.6. So you can use graphing technology in order to solve if you're really stuck as well. I can't use quadratic formula for this guy, unfortunately, because quadratic formula only works for a degree 2 equation. And since this is degree 3 and you haven't learned how to factor a degree 3, graphing technology actually works very well. So from Desmos, we had said that the answers were 2, 7.4, and 17.6. And I'd actually written down in my notes that these two were inadmissible. I think I made a little bit of a mistake. The only one that is inadmissible is the 17.6. And the reason why I know that is because if I put the 17.6 and I use that as my x variable, this side actually becomes a negative when I put 17.6 in here and start to calculate it. So you can't have a box that has a negative side length. That means that the other two, if 2 centimeters was x or 7.4, it actually would work. And so I showed that right over here with the 2 centimeters, that if the 2 centimeters was the x, you would get 26, 20, and 2 for the length, width, and height.